So it gives me great pleasure to welcome Dr. Anne Menifee, who's an assistant professor in the department. Many of you know her for the seminar series here today. And many of you know that Anne joined us not so long ago, but she's been busy teaching boards of students. So thank you for doing that, Anne. So she has a PhD from the other university in Big Ten, University of Michigan at Ann Arbor. And she also was granted a prestigious postdoctoral fellowship at Los Alamos National Lab, where she was there for a year before transitioning to Penn State. So Dr. Menifee's research interests are varied, but basically she's looking at technology and techniques for engineering low carbon energy production and carbon sequestration. Right? So I think the title for today's talk is Geochemical Alteration of Fractures and things like that. So we're looking forward to your talk. I just thought about a good fun fact about Anne, but I'll share that later.
Okay, now I'm nervous. Well, thank you very much for that introduction. It's fun to be here. As I was putting this together, I was realizing, the last time I gave anything resembling a seminar was when I had my job interview here, and then when I did my PhD defense. So crazy how the time flies. So today I'm going to be talking a lot about mineral precipitation in subsurface systems that are relevant to the energy sector. And so I wanted to the advancement not going to work. Courtney, my slide advancement's not. I don't know. No, now it's notes. Does this thing work?
That might not be working.
It's not. Yay! Okay.
Oh.
Courtney to the rescue. Okay, the show can go on. So, because I'm going to be spending a lot of time talking about geochemical reactions, namely mineral dissolution and mineral precipitation, I wanted to take a minute at the beginning to kind of define what those are so that I'm not losing people 2 slides in. So the main reactions that I've spent a lot of time studying in different subsurface situations, like I said, are dissolution and precipitation. Dissolution is a bit more straightforward. It refers to a solid dissociating into its ionic compounds. So this would be like if you dropped table salt into water, it dissociates into sodium and chloride, right? I put an example up here of calcite dissolving into calcium, which is a divalent cation, and carbonate anions. Calcite is a very common mineral in the subsurface that you'll see later on in the presentation. And then you can think of precipitation as being the reverse of that process. It's ions coming together in solution and precipitating out as a solid mineral. So you could write the same exact reaction for calcite. The kinetics and the thermodynamic favorability of these reactions are going to be different, but the basic premise of them is the same in reverse. So geochemical reactions are really important to understanding and being able to engineer subsurface environments that are relevant to a host of technologies that we care about. They're really important for things like oil and gas production and geothermal energy production, especially because big changes in temperature and pressure that are common to these production cycles can cause things to precipitate out of solution. It's also really important for CO2 sequestration, which, as Sanjay mentioned, I've spent a lot of my fledgling research career so far studying. CO2 is a weak acid, so when you inject it into a formation, it has the potential to start dissolving rocks in the formation. It can also dissolve wellbore cements, and so all of those pose threats to the integrity of a storage system underground. Precipitation is really important in low permeability systems, which is kind of where I'm going to focus the talk today, because in a low permeability system, you have limited ability for fluid to flow through the rock matrix, right? It has low porosity, low conductivity. And so you're mostly relying on open fractures in the system to transmit fluid through it. So because of that, any sort of blocking of the fracture has a much more pronounced impact than it does in a really porous reservoir. So we typically think of precipitation as being like a scaling agent that causes sealing of a fracture, but it doesn't always cause complete sealing. There are situations in which precipitates can serve to prop open fractures and kind of counteract stress-induced reduction of permeability. And under a bit more extreme conditions, the crystallization stress associated with the precipitate forming can actually be sufficient to induce tensile fracturing in the surrounding rock and propagate new fractures. But the conditions under which, each of these effects of precipitation persist are still not very well understood in most geologic environments. So we typically think of precipitation as being kind of a problem or a nuisance in the subsurface, but there are certain situations where we might want to promote precipitation in subsurface environments to stabilize something down there. And one prominent example of that is CO2 mineralization. I'm not gonna focus on the work that I'm still doing in this area today, but I did want to point it out as kind of some background of why we care about precipitation in general. And so some of you might be familiar with the idea of CO2 sequestration, which is where you're taking CO2 from a power plant, an industrial source, or just capturing it from the atmosphere through a direct air capture unit, and then injecting it underground and permanently isolating it from the atmosphere over extended, geologic timescales. Mineralization is kind of an enhanced security form of that, where we can take advantage of natural reactions in the subsurface, where dissolved CO2, which in aqueous systems converts to carbonate ions, can combine with other divalent cations in the system like calcium, magnesium, or iron, and precipitate out of solution as stable carbonate minerals. So basalts and other mafic reservoirs, there are certain types of rocks that have a high abundance of silicate minerals like pyroxene and olivine that have a lot of cations that contribute to these reactions. So in these systems, it's really important to be able to predict where precipitation will occur, because you don't want it to all, originate right around your wellbore where you're injecting the CO2 and clog up your formation and just completely cut off injectivity from the gun. So precipitation is really important. We need to understand how to prevent it in certain situations and how to promote it in other situations. But we don't really have a good ability to do that right now. It remains poorly understood, especially relative to dissolution. There's a lot of text on this slide, which I'm not a huge fan of usually, but I did kind of want to point out preemptively why precipitation has been a bit more challenging to study experimentally, especially compared to dissolution. So dissolution, you can fairly easily tweak a fluid chemistry to get things to dissolve. Typically, this involves injecting some sort of acid. I mentioned CO2, it's a weak acid. It will inject most any rock, even though the pH isn't insanely low. Precipitation requires a lot more elements to occur. In addition to having the perfect set of chemical conditions, which includes having the right saturation levels for something to fall out of solution and having sufficient pH buffering in your system. You also need a lot of elements for nucleation to occur, which refers to when a crystal nucleates and starts to grow. In the subsurface, most nucleation occurs through heterogeneous nucleation instead of homogeneous nucleation, which means that it needs some sort of solid substrate to kind of latch onto and start growing. And so the availability of nucleation sites is influenced by things like surface roughness. It's influenced by the mineralogy of your system, the chemical composition of the rock that it's forming on. A lot of things that vary significantly on small spatial scales and are very difficult to predict up front. So we find that experimentally, as will probably become evident in some of the results I show, even when, with thermodynamic models and geochemical models, we predict that precipitation should form somewhat uniformly in a pretty uniform environment, it often fails to form at all, or we see very odd behavior in where the precipitates are localized. So a lot of my work in the past couple of years has been to try to fundamentally understand where and how these reactions occur so that we can better predict them. And the main reason for that is because understanding where these reactions will occur in a system give us a lot of insight as to how precipitation will impact permeability, whether it's going to completely block off a system or, what's the critical threshold of precipitation that would seal off a fracture system versus, how much can you get away with before and still be able to maintain fluid transport. So I'm going to talk first about some experiments where we were looking at precipitation caused by fluid rock interactions, which means that you're relying on something to dissolve in the rock before something else can precipitate out of solution. And then I'll talk about some experiments that we're looking at precipitation caused by mixing of two different fluids. This idea of incompatible fluids just refers to if you have a cation in one solution and an anion in one solution, the solutions come together. Usually this is inadvertent in oil and gas operations where this is very prominent. And the solution is now supersaturated with respect to some mineral, and so it precipitates out of solution. And then CO2 mineralization, again, I'm not going to talk too much about that today, but this is another scenario where we need to understand how to maximize the amount of CO2 we can solidify in the form of carbonate minerals while minimizing the amount of other precipitation products and things like clays that form through those processes. So I'm going to start by talking about some experiments, again, looking at precipitation caused by fluid rock interactions. We are specifically interested in how the initial mineralogy of the rock and the fracture system that we're starting with impact the amount of precipitation that we get and where that precipitation occurs, and then how that precipitation affects fracture permeability, which is basically the ability of fluid to flow through the fracture system. So these were some experiments that I ran with a really great team out at Los Alamos National Lab. All of them were in the same experimental setup. So I'll give a quick SparkNotes rundown of what that entails. We are running a bunch of triaxial shear experiments inside of a microcomputed tomography scanner, which is shown over here. So I don't know if people are familiar with CT scanning, but you might be more familiar in a medical context if you've ever had a CT scan or know someone who's had one. This is the same concept except for rocks. It gives us X-ray attenuation data on a rock core, which we can use to kind of back out how different minerals are changing inside of the rock. So we put a core inside of this triaxial vessel. The entire thing is inside of a CT scanner. And in these experiments, we centered the core between these asymmetric stainless steel thrust collars, which concentrate shear stress along a central plane. And the reason for that is we wanted to create live shear fractures while injecting reactive fluid so we could monitor how reactions occur in active fracturing systems. And so from this middle image, I'm showing an X-ray radiograph, just an example from one experiment we ran. As we were running these experiments, we took continuous X-ray radiographs, which are just 2D projections on the fracture plane. And that was so that we could monitor for changes in fluid, for obvious, things precipitating or dissolving out of solution, obvious changes in the fracture geometry. And then periodically, we would kind of pause and take a full CT scan of the core, which gives you full 3D volume data. And so I'll show some of this data as I go throughout the results. So a lot of this work was motivated by some, I guess, now kind of preliminary experiments I ran when I was a grad student and had the opportunity to work out at Los Alamos. In those experiments, we were using the CT scanner to run them, and we were injecting barium-rich fluids into carbonate-rich shales while we were directly fracturing them. One of the main things we found across all those experiments was that these barium carbonates precipitated really quickly within about 10 minutes of fracturing the sample. And we saw mixed effects on permeability of the system that we couldn't really directly tie to how much mineral precipitated. So this is showing results from one of the experiments where it's a little bit grainy, so I apologize. The challenge when you try to take scans really quickly is you lose a little bit of image quality. But basically what it's showing is something being fractured. After fracturing, these little white opaque regions are barium carbonates precipitating in the sample. And you can see it's kind of filling up a lot of the fracture in certain regions. We didn't see a change in permeability in these experiments, despite the fact that we had a lot of precipitation going on. And we were also, I'll get into the full details of this experiment, but at the same time, we were increasing the confining stress outside of the core. So we were filling up the fracture with some sort of precipitate, and we were compressing the fracture together with stress, but we didn't see any change in fluid flow through the fracture. And this is because of just how the precipitation was oriented. It was unevenly distributed throughout the fracture in a way that allowed sufficient through-going fractures to maintain permeability So there, we didn't see complete sealing despite two things that kind of act in contrast to maintaining permeability. And then this is an example of another experiment where we actually saw significantly less precipitation, but completely opposite behavior in terms of permeability, which was a little bit counterintuitive. So in this experiment, the rock was much less reactive. We didn't really expect much to happen. But we saw permeability completely nosedive in the middle of the experiment. And that corresponded with the onset of precipitation in the fracture, which I'm showing with these cross sections here. And the reason that the precipitation impacted permeability so much is because it was all occurring right here at the inlet, basically sealing off the main fracture, as well as kind of the main choke point between the fracture faces. So these results kind of, then the main takeaway was that it's not just, you know, how reactive the rock is or how much precipitation you get. It's really important to understand the distribution throughout the flow system because that has a much stronger influence on overall fluid transport and fracture permeability. This is just an example of some SEM data from thin sections of those samples where we saw some really interesting localized behavior going on. So again, all of these white regions are barium carbonate precipitate. And you can see that, you know, even in a small 100 micrometer area, there are some regions that are completely cemented with the precipitate and some regions that are left untouched. And there was no, you know, distinct correlation with things like fracture aperture or surface roughness or any parameters that we could, you know, readily tie to this behavior. So all of that kind of motivated this next set of experiments that I'm going to talk about, where we wanted to use a much simpler initial composition of our rock to try to better be able to understand some of these questions, like how does the fracture geometry and how does the rock composition influence where these things precipitate out of solution. So in these experiments, I've kind of highlighted some of the main changes in conditions here. I'm just going to talk about 3 different experiments. One of the main differences is the rock type. So I've tried to simplify it a bit here. The first 2 experiments, it was pretty much just a sample of anhydrite, which is calcium sulfate, and it had minor inclusions of dolomite, which is a calcium and magnesium carbonate mineral. And then the 3rd experiment was with kind of in what I consider an opposite rock. It's primarily dolomite with smaller grains of anhydrite scattered throughout. So in all of these experiments, again, we're doing active shear fracturing of the sample while injecting some sort of reactive fluid. Here we're injecting a extremely excessive amount of barium, 180,000 parts per million, which is about 18 weight percent, which is not supposed to be representative of environmental conditions. We did this to get the reactions to occur over experimental timeframes that we could readily characterize. We also ran all the experiments at higher temperature, 50 degrees C, which is, you know, representative of a lot of subsurface environments and also accelerates reaction kinetics. And then the other thing that we varied among these experiments was the extent of shearing, which is reflected in how much the sample is displaced from its starting condition. And I'll talk about that more as I go through the results. This is just a little image of this experimental setup. Equipping the system with a heating element was actually not as trivial as it may sound, because the way the cabinet's designed, I was like physically in here, and I don't think it's as obvious from the picture, but it's kind of a confined space. So, but I got it functional, and basically it looks kind of like this with heating tape on the top and bottom. I wrapped insulation around it to maintain a steady temperature, and we monitored temperature the whole time and got it to stay within about half a degree of 50 C. So all of these cores, you know, these are just kind of some extra details. You're shearing them under 3.5 megapascals of confining stress, which is the stress that's enclosing the core on the outside. And in all of these, kind of the main experimental protocol was to shear the sample. So as soon as shear failure occurs, we then started injecting these barium-rich solutions to try to promote interactions with the freshly sheared rock. And then after shear failure occurred, we continued injecting barium chloride at pretty slow flow rate through the rest of the experiment, and then monitored the reactions with the computed tomography and radiography data. So these are some results from the first experiment that we ran, which actually turned out to be the most reactive set of conditions. In this test, we started out with an anhydrite dominant sample, so it had a lot of calcium sulfate in it. And we displaced the sample a pretty significant amount, 5 millimeters. So we generated the most complicated fracture system, and that is likely a big part of the reason why we saw the most precipitation in this experiment, because we had a lot of surface area for these reactions to occur. The displacement was actually it was somewhat inadvertent in this experiment. It was due to the rotation of the stage, but it gave us a good result, so we can't complain. These are some cross sections taken from the post-reaction computed tomography scans. So you're looking at the core sample in the direction of shear, and you can see how the precipitation was mostly concentrated at the inlet and the outlet of the core. So we saw this in a previous experiment, and it really had a significant impact on permeability. In this test, we did not see a significant change in permeability because there were enough fractures left open. You can't really tell. I should have brought the 3D data. You can't really tell as much in the 2D data. But if you look at it from multiple planes, there were a lot of offshoot fractures that were left untouched by the precipitation. And I'll also explain on this slide because I've labeled these throughout the rest of the results. Because we were dealing with a pretty chemically simple system, the CT data was much easier to interpret than it usually is. We only really have 3 minerals. So like I said before, these white opaque phases are barite, which is barium sulfate. That's what's precipitating in the system. And then the anhydrite is just part of the host rock. That's kind of these lighter gray regions. And the dolomite is the darker gray regions. Whenever you're looking at X-ray data as kind of an aside, it's looking at X-ray attenuation. So denser phases show up as lighter colors, and then less dense phases show up as darker colors. So you can see here that something with a really dense element like barium in it is a bright light, and empty space, fracture, or void shows up as black. These are some more cross sections taken perpendicular to the shear fracture of the sample. Again, you can see that some areas were totally cemented. Some of them were left untouched, which is where the fluid was continuing to flow. And we saw that a lot of these kind of smaller fractures that didn't go through the entire core were more likely to be, fully cemented by the precipitate because they weren't being subjected to continuous influx of new fluid. So after the experiments, we took thin sections of all of the cores to be able to identify the precipitates, first of all, and also to be able to look at them on a smaller scale. So this is an example of one of the regions showing kind of some of the behavior of precipitation, where it's basically concentrated in this, what we call a damaged zone around the fracture, right? And this makes sense because the samples are pretty low permeability. So fluid is really only able to get, 10 to 100 micrometers into the sample where the fracture damage has occurred. This is another just example showing some different behavior where the precipitation was totally cementing part of the matrix, as you can see by the white material up here. Okay, so we ran another experiment with basically the same type of rock. One of the challenges with working with real rocks is you never, unless you're doing 3D printing or something, you never get the exact same rock twice. But these came from the exact same well, and chemically they were compositionally identical. So we started with the same rock. The only difference in this experiment was that we maintained a much smaller displacement, less than 1 millimeter. So the fracture turned out to be much cleaner and neater and smaller than the first one was. And so with that, we saw less barite precipitating in the fracture. You can kind of see from this image here that it's not really filling the fracture, it's just kind of coating one of the walls. We saw that throughout all of our CT data. So these are some more examples of that. And then in the SEM data, we saw less precipitation overall, but it kind of behaved the same as the first experiment. One of the interesting kind of observations that we had in these experiments is that we saw a lot of dead-end fractures that were completely cemented with precipitation. And so this is something that we're working to understand on a bit of a smaller scale where we can actually look at these reactions play out in real time, is whether the reactions in a fracture are proceeding uniformly, or if it's a situation where precipitation starts at the dead end of a fracture and then works its way inward, which is actually something that I saw with my previous basalt work, that it started at a dead end and then kind of worked its way toward where the fluid was coming from. This is another example of SEM data for this experiment. Again, it was kind of a little bit haphazard whether precipitation was cementing a fracture or just kind of floating along the edges, coating the edges. And unfortunately, there was no direct relationship between the aperture, which is basically just the width of the fracture, and the behavior of the precipitate or the likelihood of precipitation to form in that fracture. So that's something that that I'm trying to work on now with some modeling efforts, is to be able to use characteristics of a fracture and the underlying mineralogy to predict the likelihood of precipitation. Because it's not just a physical effect of fracture aperture. That'd be really easy if it was, because then you could really directly put that into a permeability model. But it's also a function of very, very small localized chemical effects, which are very difficult to kind of predict in real time. Okay. So then the last experiment in this set that I'm going to talk about was same conditions, but the opposite, I'm calling it the opposite rock, where it's primarily dolomite, it's calcium magnesium carbonate, and then there were smaller grains of anhydrite scattered throughout. And so because anhydrite turned out to be the most reactive mineral in this rock, as I showed in some of the previous slides, most of the precipitation was actually forming on the anhydrite and not the dolomite. And we only identified barium sulfate precipitating in the SEM data. We didn't see any barium carbonate. So running an experiment where we had mostly anhydrite and just a little bit of dolomite, or sorry, mostly dolomite and a little bit of anhydrite, kind of highlighted the localization of these minerals in the rocks. This is a little bit more evident here. It might be a little bit grainy on the PowerPoint screen, but basically, the anhydrite grains are these lighter regions here. Dolomite is the rest of the rock. And the results for this test were pretty interesting because the barite within the same fracture was only forming where the fracture intersected the anhydrite grains. And this is something that we also want to work to better understand, whether it's something with reducing the nucleation energy barrier because it's a sulfate mineral precipitating on a sulfate mineral, or whether it's just that the chemical conditions are so localized that, like, as soon as sulfate dissolves, it precipitates kind of right at the source. But it was really a consistent result throughout all of these experiments. This is one of the SEM images kind of highlighting that. You can see we have this giant anhydrite grain, or a larger anhydrite grain over here, surrounded by dolomite. And again, within the same fracture, we really only had precipitation occurring within the anhydrite grain and not touching the dolomite. This is an example of the same thing. I like the SEM images, so I think I got a little too excited putting them on here. Okay, and from my perspective, this was really interesting because the kind of general result from these experiments was very consistent with behavior I saw in previous work looking at CO2 mineralization in basalts, which is a totally different system. This is just kind of a snapshot of a result from experiments I was doing injecting CO2 into basalts. And basically the CO2 was dissolving cations from the rock, like calcium and magnesium, and then those were precipitating out of solution as carbonate minerals. And so what I'm showing here is that most of the carbonate minerals that precipitated, so the things that bind to CO2, were forming directly on the source of divalent cations in the rock. So pyroxene is a silicate mineral. This is the formula right here. That was the most reactive source of divalent cations in the rock. And throughout the experiments I did with basalt, I saw that precipitation almost exclusively occurred at the source of divalent cations that were forming the precipitate. So this is something, like I mentioned, that we're still kind of working to understand. I think it's really important because if we can understand, but if we can predict where precipitation occurs, we can better understand how it's going to impact, permeability within a larger fracture network. And so I think this observation is important. We just need to better understand the mechanism behind it. Like I said, in these experiments, we had barium sulfate precipitating in a system where we were injecting large concentrations of barium, and then smaller amounts of sulfate were dissolving from the rock. It's analogous to what I saw with basalts, where we were injecting CO2-rich fluids, small amounts of calcium were dissolving from a rock, and then calcium carbonate was precipitating out of solution. So it seems to indicate that whatever the kind of rate limiting ion is for the precipitation reactions to proceed is where the precipitation has a strong localization toward. Another, outcome from these experiments, first one was very intuitive. We expected the temperature would increase the rate of precipitation because it has a strong impact on reaction kinetics. And we also found, that we got more precipitation when we fractured things more heavily. So when there's more reactive surface area, you tend to get more precipitation. Theoretically, reactive surface area is directly tied to your kinetic reaction rate. So that made sense as well. And it also is tied to nucleation kinetics, which is really important for precipitation. So we know a lot of the ingredients that are required for precipitation to start and proceed, but it's still really hard to predict it with certainty in subsurface systems. And I think one of the main challenges is there's no, one or two variables that can kind of give you a good indication. It's a combination of geochemistry, thermo, geomechanics, a lot of things that are kind of difficult to map onto one model with any computational efficiency. Okay, so I'm going to switch gears now, spend a few minutes talking about some other experiments we did where we were kind of approaching precipitation from the opposite angle, where instead of trying to react different fluids with the rock, we're looking at mixing two fluids and getting things to precipitate out of them. And then I'll kind of wrap up and leave plenty of time for questions. So in these experiments, one concept that we wanted to better understand is this idea of fracture matrix communication. So I mentioned in the beginning that in low permeability systems, you're relying on fractures for fluid to flow, right? And so you would expect if most of the fluid is flowing through the fractures, that's where most of the reactions are going to be concentrated. You're not going to see, things precipitating really deep into an impermeable matrix. So in these experiments, we kind of wanted to get at this question of, how much of the matrix is contributing to the reactions? Is it all just occurring in the damage zone of the fractures, or do we see additional diffusion beyond the fractures into the matrix that's contributing to dissolution or precipitation? And so the two main avenues through which fluids in a fracture can communicate with the bulk matrix are diffusion through the fracture phase, where you have a bulk fluid over here, and you have slow diffusion of different aqueous species into the bulk rock matrix. And then advection, which primarily occurs if you have either pre-existing faults in the rock or you're actively fracturing the rock and you generate some sort of fractured zone or damaged zone where fluids can now ingress from the fracture into the matrix through an advection process. Diffusion is notoriously much slower, and it's also much more limited in low permeability systems because the pores are not well connected. So there's usually a pretty thin barrier beyond the fracture face where you can actually have fluids penetrate into the rock. This is an example of diffusion from a group in Slack that came out a few years ago where they were looking at precipitating barium sulfate in static systems. They were putting shale chips basically in fluids that were super saturated with respect to barite and saw it precipitate on the surface, but not really ingress deeper into the rock. And then this is an example of what we've seen with this kind of advection process where you generate a lot of fault gouge and damage through active shear fracturing. And you see an extensive amount of precipitation that kind of is allowed to go deeper into the fracture where the extent of your fracture damage zone is. So for these experiments, we used the same experimental setup where we're again, injecting a reactive fluid. But instead of trying to react the fluid with the rock, we pre-saturated the samples with a solution of sulfate and then injected different concentrations of barium to try to get the barium in the injected fluid to react with the sulfate in the pores of the rock and precipitate out as barite. I guess I'll mention one of the main reasons that we are focusing on barite or just barium in general is because, like I mentioned before, barium is super dense. So it shows up really well in the X-ray images. And barium sulfate in particular is one of the most notorious scaling agents in hydrocarbon production operations. So it has a lot of relevance to field settings. So I won't go through the protocol in detail, but basically we dried the cores, saturated them with sodium sulfate, sheared them under different conditions. The main thing that we buried in these experiments was we ran 3 of them at ambient temperature and then raised it to 50 C. And then we injected different concentrations of barium chloride into the sample. So these were all done on Mancos shale, which is just, they're all the same type of shale is the main thing you need to know there. And they had different levels of displacement, but that wasn't really a huge factor in these tests. So the first experiment was pretty disappointing, despite the fact that we had saturation levels that were, or saturation index that was much higher than the previous experiments I mentioned that had seen precipitation in a static system. We didn't have any precipitation in this system, either in the XCT data or in our SEM analysis of the thin section. So I won't belabor that experiment because it was kind of a negative result. So we tripled the concentration of barium in sulfate. Now we have an even higher saturation index, which is kind of the chemical indicator that something can precipitate if the saturation index is greater than 1. And still no precipitation at the end of this experiment. But I decided to soak this core for a few more days, so just kind of sitting in its barium and sulfate solution. And at the end of that test, we did see some small evidence of precipitation forming in some of the smaller fractures, but we weren't really able to confirm that well with SEM. And another interesting observation from this experiment after the soak was we kind of saw, I don't know, again, how well you can see it in the screen, but we saw this kind of reaction halo forming around the fracture where you had this white opaque region that looks like kind of a ghost of a precipitate forming at some distance from the fracture. So we tried again, we increased the barium concentration by 4 times and kept the sulfate concentration the same. Again, no precipitation, but we saw the same kind of reaction halo effect forming, which was pretty interesting. And I'll circle back to that in this last experiment. So when we kept the same concentrations and heated the sample to 50 C, we finally saw some defensible precipitation in our system, which is just, this is an example of it. And we were able to confirm that with SEM, but it wasn't anywhere near as significant as we've seen in the experiments that I showed before, despite the fact that we had, really high saturation indexes. Again, previous experiments found barite precipitation at a saturation index of, I want to say 1.3, which was much lower than what we were working at. But the reaction halo thing was one thing across all of the experiments that we thought was interesting. At first, we kind of wondered if it was a scan artifact or, just something that wasn't a real phenomenon. But the fact that we saw it in 3 experiments indicates that it's probably real. And our best hypothesis right now, because we haven't been able to identify it with imaging data, is that it's basically ingress of fluid into the damage zone. So a fluid that's rich in barium will show up denser than other fluids in the X-ray data, but it's not going to be as bright as a solid precipitate of barium. So we didn't quite get what we were looking for in terms of precipitation serving as kind of a tracer for these reactions, but we did see some evidence of where the barium-rich fluid was moving into the matrix. This is very, very lackluster SEM data showing where we identified some of the barite in the system. We found a lot of barite that was below the XCT resolution. So, the XCT data wasn't all inclusive, but it was still not as much as we've seen previously. Okay, so one of the main takeaways from these experiments, the results were kind of a negative result because we had anticipated having enough precipitation that we could use it as a tracer to get at some of our questions about how fractures communicate with the matrix. And we mostly just didn't see precipitation, but I decided to include them because I do think it kind of highlights how challenging these systems are to study and how hard it is to design a system where you get the reactions to occur, much less study the influence of the reactions on other parts of the system. And I think that's why it's been so difficult to get at these questions of like, under what conditions does precipitation impact permeability? Because it's really hard to control the amount and type of precipitation that you need to be able to study these questions experimentally under relevant subsurface conditions. Yeah, and I think it also kind of points to kind of a known challenge in modeling right now is we have really good models for fluid transport, We can do reactive transport modeling where we're accounting for both transport and chemistry, but those models don't have a really good way of accurately predicting precipitation reactions, because it involves concepts from so many and processes, I guess, from so many disciplines that are really challenging to accurately incorporate into one model, and also rely on a lot of or depend on a lot of small scale heterogeneities in the subsurface that, you know, are really, really hard to map with any sort of strong resolution. So to conclude with some, I guess, takeaways from the precipitation work, I don't know if idiosyncratic is the right word, but it's kind of the word that comes to mind from my perspective in trying to work with these systems. There's a lot of factors that very clearly have an influence on when precipitation occurs and how much occurs. Things like temperature, the saturation index, and the pH of the system. Transport conditions, we tend to see more precipitation where transport is limited to diffusion, where you have low flow rates and high residence times for things to kind of almost incubate and react. And we also see more precipitation in kind of our really heavily fragmented areas or regions where you have a lot of reactive surface area for things to nucleate and dissolve. But there's no, you know, distinct set of variables that you can succinctly tie to precipitation. So this is one of my areas of research I'm working on right now, mostly tied to mineralization, but also to precipitation in general, is to be able to survey a set of initial conditions, predict how much mineralization is going to occur, predict the change in aperture, and then once you can understand the change in aperture throughout an entire fracture network, you can start to predict how the overall permeability, bulk permeability of the system will evolve. And so another key takeaway that I bulleted down here is that a lot of models do a good job of kind of telling you, you know, based on this concoction, this is how much mineral could precipitate. But it's actually often more important to predict where in a pore system or a fracture system the minerals will precipitate, right? Because that has a stronger influence on permeability. If you get a tiny bit of precipitation, but it's at a critical fracture intersection, it could be a showstopper for your entire operation. As opposed to, you know, you could get a lot of precipitation, but maybe it's just coating fracture surfaces. And so you still have a bit of a constricted fracture, but you still have the ability for fluid to flow. So this is important in understanding permeability in any sort of subsurface reservoir, injectivity, especially in low permeability reservoirs where pressure buildup is concerning. And, you know, in the context of CO2 mineralization, if you're trying to convert CO2 to a solid, which is kind of is where my heart is in research, then you need to understand these reactions to know how much you can solidify in a given system and how much you can keep injecting before you have a critical loss of permeability. Okay, oh wow, that was like almost right at 45 minutes. So that's all the content I have. It's just an acknowledgement to all the people I worked with. Most of these, a lot of the analysis I did here at Penn State through the use of the fantastic equipment and resources at MCL. But the experimental work that I showed, I did in the year I was at Los Alamos through this director's postdoc fellowship program that Sanjay mentioned, which was a really great opportunity. So yeah, I'm happy to answer any questions. And Sanjay can share his fun fact.
So the ability to predict where precipitation is going to occur is misleading you in a sense because you're still trying to work on about it. I think you very clearly show that aperture as a whole will not be a good predictor. And I think it's because aperture is a very local measure when in a fracture network you count to see more visually how that aperture affects your flow profile. So I think you've also shown that in some cases where you would imagine that your velocities are very slow, the likelihood of precipitation is higher, and when you have these restrictions where flow still needs to pass through, then it's not enabling that precipitation to form. So I would encourage you to maybe try some of the data that you have and construct maybe a or fluid dynamics model, or something that will give you a sense of velocity profiles. Maybe those velocity profiles with the velocity map can be a good predictor of, or at least an indicator of the likelihood of that precipitation form. Because yes, small, apertures sometimes can be equated to places where flow is not happening because of the dead end, and then precipitation will occur. But in some cases, it can be a restriction, and the flow needs to pass much faster. So that's something that you can try. And I see that you have a case where your precipitation seems to be more evident, where you have this anhydrite region in the sample that had most dolomite, and you're trying to attribute that some of that to the geochemistry. I would like to propose that maybe something that can be happening is that the difference in mineralogy is affecting the shear failure, and the shear failure is creating more intricate, fraction patterns, and that's what's creating it, not necessarily directly the chemistry of it. So just something to think about. I thought it was very interesting.
Yeah.
It's just very close to my heart in terms of.
Right. It could be the case. Yeah. I mean, from going through, all of the 3D data as well as the SEM data, there didn't seem to be distinct differences like along that fracture path when it intersected different mineral grains. But I can go back and look at it with that kind of perspective to see if it made a difference. And just looking up like the strength properties of both of those minerals to see if like we would expect a significant difference in failure rates. And that's a really good comment as well, your first one on the computational modeling. I did something similar to that with my basalt work, which I didn't show in this presentation, but taking the 3D CT data and then incorporating that into flow models to get permeability and flow velocities along the fracture paths. So yeah, I think that's something that I should probably couple with these experiments as well.
Also, I think going back to what Elena mentioned, seems like the dominant mechanism to change. You have inlet precipitation, maybe because of pressure gradient velocity, but precipitation at the outlet then will be controlled by other things. Right? And I think even a simple dimensionless group kind of study, you don't want to invest your time doing a computation of fluid dynamics, just to understand what may be the dominant groups in the parts. And I think you have this data. But I do have one question. So I think the results that you show of precipitation by mixing of fluids, do you think, I would think that that's an intriguing solution for engineering fracture sealing. You have always this fear that your injected CO2 might migrate into the caprock and then off. Do you think it's an intervention technology? You can selectively drill into the top of your formation and induce precipitation and fracture so that you're pretty much sealing the CO2 in place.
Yeah, absolutely. I think people have proposed a lot of different ways to do that. I worked on a proposal recently proposing to leverage microbial induced calcite precipitation, which is basically there's certain microbes that can catalyze precipitation of calcite. We are proposing to kind of spike systems to have this occur in shales such that you can kind of selectively seal off permeability where you're using it as a cap rock. I'm not sure in a subsurface system. It definitely takes some intricate engineering, I think, to really target these at, like, you would have to have pretty good resolution on where your leaks were occurring to be able to kind of seed the precipitates and figure out, how to distribute them, like you're saying. But, that is something people are looking at. And I've also seen the idea thrown out by others of some sort of like temperature coded seeding materials where you inject it, you kind of fine tune the coating to dissolve at a certain temperature. And then once it dissolves, it interacts with CO2 or some other major compound in your pore fluid and precipitate. So it's kind of this idea of, what's it called, like a geofence or something, where you're kind of spiking a system and trying to tune the chemistry in ways that you can to induce precipitation at, certain intervals. So I definitely think maybe that's, kind of the future of containing things in the subsurface with a bit more security. But yeah, to my knowledge, it's still kind of a loose concept out there. Well, their experimental setup was they basically had batch reactors where they were putting in shale chips, and then the shale chips were just sitting in solutions that were super saturated with respect to barium and sulfate. So they had sodium sulfate and barium chloride at much lower. They were like 2 millimolars of barium and 0.06 millimolars of sulfate in those solutions. So it was a much smaller concentrations than what we were doing. I wasn't necessarily trying to mimic those. It was just kind of where I started from. You know, they were really interested in barite. I had some conversations with them, and they really wanted to. They were really interested in kind of how those reactions would play out in a real system, as opposed to something just sitting there and minerals depositing on it. They kind of wanted to see, you know, how the precipitation processes started and evolved. And I was already doing similar work in this area. So in my head, I was kind of like, oh, well, if we just start with a little bit higher concentration, and they're already seeing this in just a static system where you're not really doing anything to kind of promote that reaction, it's just occurring on the surface of these samples. I thought for sure kind of in this system, we would see something, but it turned out to be a little bit less effective than I anticipated. So I think one of the main reasons for that, honestly, the way I designed the experiments, is that you are relying on the shear fracture to intersect enough of the saturated pores to release enough sulfate for the reactions to occur. Whereas in their system, they had the barium and sulfate directly in this bulk solution, where the amount of solution far outweighed the amount of rock. Whereas in our experiments, it was kind of the opposite, like the fluid was a bit more limiting than the rock. So I think, you know, if I don't know, if I'd used either a much more porous sample, which then kind of starts to get away from like the realness of the system, or if there was a way to kind of, you know, co-inject barium and sulfate, you know, maybe if I'd done alternating injection. The reason I didn't do that is because these experiments are very tricky, because I wanted to get precipitation inside the rock while getting no precipitation anywhere in all of the flow lines that go into this, because it basically with barite, it's very recalcitrant and very difficult to remove. So if you have barite precipitating in your system, it doesn't really, acid flushing is not really effective. Like you basically just have to throw out that part of the system. So anyway, that's a very long-winded way of saying the experimental conditions were very different. I think there's pretty clear reasons in my mind why ours was much less effective than theirs. But at the same time, when I started the experiments, it seemed like a good way to kind of take, you know, a smaller scale observation and see it play out in real time in a more active system. No, I don't think so. Yeah. I don't think so. I mean, compositionally, we were starting with really similar shale cores. Permeability was really similar. So yeah, I think it's mostly just differences in the effective fluid saturation based on how much of the pore space we were able to intersect during fracturing events. That's kind of my working hypothesis, but yeah. No, so are you talking about soaking after the reaction? Like here when I did this? Oh, no, these are yeah, maybe I should have clarified. So all of the experiments like here with these kind of anhydrite and dolomite cores, the CT scans I'm showing were the last scan I took inside of the core vessel. So this was just at the end of the experiment. The experiments were pretty short. They were, well, I say short, these things take like a week to set up. But the experiments themselves, like we only kept injecting fluid for maybe 3 to 4 hours after shear failure occurred. So that's when these CT scans were taken. And it was obvious there was enough precipitation in these experiments that I could see it in the X-ray radiographs, like the 2D projections that I was monitoring during the experiment. And so because I knew I had a lot of precipitation, I kind of just didn't bother with the extra soaking step. I cared more about like what occurred kind of in the immediate vicinity of the shear fracturing. So. Yes, I have. Yeah, I have higher resolution scans that I've been using for like, which yeah, I didn't show a lot of the try to focus on pictures. I don't know if that's better or worse. Maybe we're engineers and you like equations more. But I'm using like the higher resolution scans to get to segment out the precipitate and the fractures after the reactions. And that's something that I would use and or be able to use probably a little better in a velocity or computational model like Selima mentioned. Eugene. That's a good question. I think it's hard to answer because we stopped shearing the samples around the time or just before the precipitation started. But yeah, I think to get at that question, we would have to keep applying axial stress after that. But it would be really interesting to see. The reason I didn't do that is because the goal of these experiments was to get precipitation, and it's I don't know, it was a little bit harder than it looked. Like there were a lot of other experiments that yeah, don't even make this because they just aren't successful. But so once I got precipitation, I didn't really want to risk like obliterating it because of the types of analyses I wanted to do after the reaction. But that is an interesting concept, and I think, you know, it would be something that would be important to look at, like we're talking about with this targeted permeability control or microbially induced calcite precipitation or some other form of induced precipitation to kind of seal up a fracture. You would want to see, you know, how does the stiffness or the strength of that fracture compare to what it, you know, would have been if it was the whole rock as opposed to a rock with something else infilling it. So yeah, I don't know if that's at all what you're talking about, but I think, oh yeah. Yeah, that's a really good point. Yeah, I could do some testing on it. Those kinds of tests are a bit destructive, so I have to use them selectively.